Okay, welcome everybody to this event. The subject of my talk will be more or less a connection or analogy between two sets of interesting physical and mathematical objects. On one hand, it's going to be conformal field theory, which in general can be in d dimensions, and on the other hand, it will be the spectral theory of automorphic forms. So I'm just going to write automorphic forms, but its emphasis on their spectra and the associated L functions. Now, there already, of course, exists some known connections between conformal field theory and modular forms or automorphic forms, notably in two-dimensional conformal field theory, where the partition function of 2D CFTs are essentially modular forms, or versions thereof. But this connection, which the connection that I'll focus on today, which was, to my knowledge, first pointed out in this generality in this paper that I wrote with Kravchuk and Pal. Pal is in the audience, I think, so we're there. So this connection has a rather different flavor between compared to the connection between, say, 2D CFTs and modular forms, in the sense that it's rooted very firmly in representation theory. So both of these two subjects are rooted very much in representation theory. In particular, the CFTD is rooted in representation theory of the Euclidean conformal group. So in this case, it would be SO1, comma D plus 1, which is the Euclidean conformal group of the dimensional of the D sphere. And as has transpired over the last, say, 50 years or so, it is also the subject of automorphic forms is most naturally formulated in the modern language using the language of representation theory. So this is somehow why this analogy fits very nicely into the modern view of automorphic forms, and it connects ideas in conformal field theory to many ideas in contemporary mathematics, number theory, and spectral geometry. So, hopefully on the long run, this is going to shed a light on the so far rather mysterious mathematical nature of conformal field theory in d dimensions. But what I'll focus on today is rather using methods and ideas that we already have developed, that people have developed before us in conformal field theory, namely conformal bootstrap, and proving some new theorems, new rigorous results on the other side, so on the side of number theory and spectral geometry. So specifically, the application of this kind of transfer of ideas that I'll focus on today was written up in this paper with many authors that came out in August, where we applied some rather well understood techniques in the conformal bootstrap to L functions. So now I'm going to review what all of these ingredients are, what L functions are, and so on as we go on. We have, I guess, still more or less 2 hours. And so what we actually proved a result which is of modern interest in the theory of L functions, a version of a subconvexated bound, so a rather strong subconvex bound on L functions. Okay. So somehow the goal of this lecture, of this course, is to explain what are all of the ingredients, to understand and state the result, and that'll be mostly in the first part. And in the second part, I'm going to explain how we actually used ideas from conformal bootstrap to prove this. And so I will not explain in much generality this analogy between CFTs and automorphic forms, but I'm going to rather illustrate on the particular examples as I go on. So somehow the goal is to be very pedagogical and really explain what all of these ingredients that go into this proof are. Okay, and afterwards, if you want to know more about conformal bootstrap, there's going to be a talk by Balt, and if you want to know more about, say, automorphic forms or spectral hyperbolic surfaces, there's going to be the talk by Frederick. The plan is the following. There'll be roughly 4 parts. The first 2 parts will be a review of some basic material in mathematics. So I apologize to the mathematical experts in the audience, because this is probably going to be quite slow for you. First, I'll review the necessary or the relevant ingredients of the theory of spectra of hyperbolic surfaces. Then in the second part, I'll review what I'll need to explain about L functions. So hopefully this will take about an hour. Then I'll explain the conformal bootstrap method as applied to this problem. And then finally, I'll explain how we use the conformal bootstrap method to prove this state-of-the-art result on L functions, which is a while bound on the triple product L functions. Now I should say that of course this idea of this connection between CFDs and forms didn't really come out of nowhere. In particular, we were strongly inspired by previous work by Bonifacio and Hinterbichler, also Bonifacio on his own. And rather remarkably, it turns out that a very similar method was developed independently by number theorists, Bernstein and Reznikov, who, as far as I know, didn't know anything about a conformal bootstrap, but they developed a very similar looking method for bounding L functions. But in our paper that I review, we were able to kind of use what we know in a conformal bootstrap to actually improve on their result. So the methods are very similar, but somehow the explicitness of the conformal field theory computations allows you to go beyond what these number theorists, Bernstein and Reznikov, were able to prove. I should also say, please feel free to ask questions at any point.
In the paper by Bonifacio and Hinterbichler, was there an automorphic form aspect, or is it purely spectral, Einstein manifolds?
Right. In the original paper by Bonifacio and Hinterbichler, they were looking at more general class of manifolds, hyperbolic, so Einstein. But then there was another paper by Bonifacio where he specialized in hyperbolic manifolds, and he didn't emphasize the number theoretic or say automorphic aspects, but he was writing down essentially the same equations that would follow from the bootstrap method. All right. So with that, let me start with one. So spectra of hyperbolic surfaces. Like I say, I'll try to be very, very pedagogical, so my apologies if this is too slow, but hyperbolic surface for me means a Riemannian 2 manifold with constant curvature, constant negative curvature that we are going to normalize to -1, or if you prefer talking about a Ricci scalar, then in this normalization it's -2. And there is precisely one such manifold, which is all of connected, complete, and simply connected. And is the hyperbolic plane, which I'm going to denote by H. And it has the following metric: ds squared is dx squared plus dy squared over y squared, where x is any real number and y is positive. So we are in the upper half plane. Okay, what happens if I push that too high? Is there some? Oh, okay. Now, an important fact about this space is that what is the group of its orientation preserving isometries. So the orientation preserving isometries of this hyperbolic space is the group PSL2R, which acts by Möbius transformation. So if we take an element A, B, C, D up to plus or minus 1, that's why there's a P, which acts on Z. So Z is, let's write Z to be x plus IY, and it sends Z to the Möbius transform of it. Okay, and this is the full group of orientation preserving isometries of the space. Okay, it's quite interesting, but not as interesting as the more general manifolds. And the ones that I'll be interested in today are those where we drop the simply connected requirement. So connected complete. So our manifold then is a quotient of the hyperbolic space or hyperbolic plane by a discrete subgroup of PSL2R. Okay. Such groups are also known as Fuchsian groups. Gamma in that case is the fundamental group of the surface M. And I'm also going to restrict to the situation where the volume of the quotient is finite. So I'm going to denote or the area. I guess we are in 2 dimensions, so I should be calling it area. I'm going to denote the area, which is computed with respect to the measure following from that metric, is finite. So in that case, gamma is also called a lattice. And in this case, gamma needs to be, of course, infinite, because the area of H is infinite. So if you want this to be finite, gamma needs to be infinite too. Gamma is infinite, but it's finitely presented. So it has finitely many generators subject to finitely many constraints. And somehow the point is that there's a very large kind of a large set of these gamma. So we can easily produce a large class of interesting manifolds. Kind of in a similar, in the analogy, these hyperbolic manifolds are analogous to CFT. So there's also supposed to be some kind of a nice large set of CFTs, but each of the elements of this set is somehow has various nice mathematical properties. Can exhibit chaos and so on. So which I'll discuss soon. So also I should say that I'm going to allow gamma to have elliptic elements, so elements of finite order. To have so there can be G in gamma such that G has some finite order, and this corresponds to the surface, not actually being a surface, but being an orbifold. So the surface can have elliptic points, which arise from fixed points of these elements G. Okay, so this is the setting in which I'm going to be talking about. Most of the discussion that I'll follow from now on will restrict to the compact case, so where H mod gamma is also compact, but it's not really necessary. I'm going to make some comments later on when things are compact, when things are non-compact, and what changes. Okay, so are there any questions for now on? For now? All right, so. Well,
is finite, but you say it may not be compact.
Yes. So actually the example which I was able to write down, which is SL2Z, is exactly of that sort. So that's an example of a finite volume non-compact case. Right? So that's everybody's favorite example, where gamma is SL2Z, but because we are working projectively, it's really PSL2Z. So just SL2Z modulo the center, which is of course a subgroup of PSL2R, so it gives rise to a surface. It's not so hard to see that it's also a finite volume. You can just compute the volume if you want of the fundamental domain. Here the generators are the famous S and T. So S takes this form, T is this matrix, and gamma is generated by S and T, subject to S squared being identity and ST cube being identity. Okay, so that's probably the simplest example of what I'll be talking about. Of course, the quotient H mod gamma in this case is not compact because there is a cusp at infinity, which essentially comes from the fact that this generator T has an infinite order. But it's quite easy to generalize this kind of group to produce many compact examples. So these are the so-called hyperbolic triangle groups, which you can describe in the following way. So you take 3 geodesics in the upper half plane. So geodesics are semicircles. Okay, so this is example 2, which is hyperbolic triangle groups. Let me denote them as gamma ABC. So they're labeled by 3 positive integers. And they are constructed as follows. So you draw 3 geodesics in the upper half plane, which meet at a triangle, and let the interior angles in this triangle be pi over A, pi over B, and pi over C. And then this gamma is generated by the 3 rotations around these 3 angles around these 3 points by angles 2 pi over A, 2 pi over B, 2 pi over C. So the fundamental domain, essentially because there is a doubling of the angle, the fundamental domain for this group is two copies of this triangle glued together. So you can kind of imagine reflecting this, and then, is there a color?
ABC are integers?
ABC are integers, yes. And then the fundamental domain is this, well, in general it can be a quadrilateral because here I drew it as a right angle. It doesn't have to be a right angle here, but you probably get the idea. So it's a sphere with 3 punctures, which are 3 elliptic points. And the presentation of this gamma is written using the generators, which are the rotations around these 3 points. So let's call them x, y, and z, where x to the a is identity, y to the b is identity. So these are the 3 rotations. Z to the c is identity. And also, if we go around the triangle and rotate, we get nothing. So this is the presentation. It turns out that this object exists precisely when this triangle has a positive area. And there's a nice formula for the area of this triangle, okay, of this ABC, which is pi times 1 minus 1 over a minus 1 over b minus 1 over c. So such a group exists precisely when AB and when this area is positive. PSL2Z is a special case, which corresponds to 2, 3, and infinity. Right? So the 2 is the S transformation, 3 is the ST, and infinity is the T transformation. This one is, of course, non-compact, but as long as all A, B, and C are finite, this is a compact surface. So in general, it's important to distinguish kind of the topology and geometry, because there could be a moduli space at a fixed topology, and the topology is specified by the following data: is the genus. So now I'm talking about general surfaces as I define them. So the quotient of H by lattices. Topology is the genus G. The degrees of the elliptic points. So let me call them n1. So these are some finite degrees of the elliptic points. There are elliptic points, and finally Q. So these are degrees of elliptic points. And finally, Q is the number of cusps. So this is kind of the number of generators of infinite order. And so for a fixed topology, there could be more than one inequivalent hyperbolic surface. Here we saw that there's only one because it's a sphere with 3 punctures, so there is no moduli space. But in general, there is a moduli space whose complex dimension is 3 times the genus plus the number of elliptic points plus the number of cusps. Oh, sorry, minus 3. And there are various things that happen when we take some limit. For example, when the G goes to infinity. I believe Frederick will talk about what happens at large genus in his talk. Okay, so this is somehow the lay of the land of hyperbolic surfaces. There's a topology. At each topology, there could be a moduli space. But so far, there is no connection to number theory. The connection to number theory comes from realizing that there's a nice discrete set of points in this moduli space which has nice number theoretic properties. This is probably obvious to you if you know something about SL2Z and you know that modular forms for SL2Z play an absolutely central role in number theory. But SL2Z is not the only example of number theoretic interest. So there is a notion of arithmetic. So there's a notion of arithmetic surface. Or I'm going to just refer to surface or gamma interchangeably because they are the same up to conjugation of gamma by PSL2R. So basically, arithmetic gamma is some countable. There's some countable set of gammas which can be defined number theoretically. And actually, the definition is a little bit complicated. It involves something called quaternion algebra. And I don't really want to go into the details of this definition, but they are basically even special hyperbolic surfaces than the general hyperbolic surface. And for example, among these hyperbolic triangle groups, there are only finitely many of them which have this property. So out of infinitely many gamma ABC, there are I think 85 such which can be defined using quaternion algebras, and therefore have relevance for number theory and for constructions of L functions.
Can I ask a question?
Yeah.
So if you don't restrict to this arithmetic, what happens with these odd gammas inside the moduli space?
If I don't restrict to what?
So now there appear three things. There is this moduli space.
Yes.
Then there are gammas. So I understand. Is there one-to-one correspondence between gammas and all points in the moduli space?
Yeah, the points of the moduli space are in one-to-one correspondence with equivalence classes of gamma up to conjugation by elements of PSL2R. So if you take a gamma, which is a discrete of finite covolume, then you get a hyperbolic surface, but you get the same hyperbolic surface if you conjugate gamma by any element of PSL2R. It's just kind of like a translation in the hyperbolic plane. And the moduli space is the set of these equivalence classes of gamma up to conjugation. And these gamma ABC are just special points in this moduli space, which are isolated.
What was the statement about arithmetic gammas? Why did he do that?
Arithmetic gammas are those which number theorists care about. And I don't, there's a precise way to define them. You start with some number field, then you specify quaternion algebra over that number field, and then you pick a maximal order in the quaternion algebra, and the group of units is gamma. So there's a precise definition, but it's a bit too detailed too long to explain. But arithmetic gammas are those such that modular forms for those gammas lead to L functions with an Euler product and functional equation. So that's. Sorry, say again?
Right after G, you wrote two numbers and you said it's some degree.
Oh, so yeah. So N1, I mean, this is not going to be too important for the rest, but it's just, so N1, these are the degrees of the elliptic points. So there's a finite number of points where there's a conical deficit, and N1 is the degree of the conical deficit, and Q is the number of cusps. So the elliptic points kind of infinite order.
I guess in none of your the few examples you've given, the dimension of the marginalized space is always 0, right?
Yeah, for all of these gamma ABC, it's 0. That's right, because it's a sphere. You can just plug in. So G is 0, and R plus Q is 3. In that case, so the dimension is 0. All right, so now let's talk about automorphic forms. So automorphic forms are basically, in the way I'm going to talk about them, which is kind of the classical point of view, automorphic form are functions on these surfaces. Or sections of bundles on these surfaces which satisfy various other nicety properties. And the probably most familiar one are the holomorphic modular forms. So definition, holomorphic modular form. So these are holomorphic functions on the upper half plane. So F is holomorphic, which satisfy an appropriate invariance under any element of gamma. So modular form for gamma is such that f of z is the same as this transformation of f. So if this m is called the weight of the modular form, or 2m. So I'm going to denote the weight by 2m. So usually 2m is called the weight of the modular form. Now, if m is 0, then the function is just invariant, so it's a genuine function on the surface. Of course, there are no such holomorphic ones, so you need m to be positive, actually. But somehow I should say, so this is the complete definition when gamma is co-compact, when the quotient is compact. And for what I'm going to talk about in the non-compact case, I actually want a notion of a cusp form. M is an integer. Yeah, so it turns out that the space of these is always finite dimensional, and it's 0 dimensional unless m is a positive integer. So in the non-compact case, there is a notion of a cusp form, where we also require that f of z or f vanishes at the cusps. But okay, don't worry about this too much, because I'll mostly talk about a compact case, but it's important to know how it fits into the SL2Z story. So at the cusps, and somehow this in particular means that f is square integrable in an appropriate sense, and in a compact case, everything is automatically square integrable. So in some sense, all holomorphic modular forms for compact cases are already cusp forms. So we don't have to worry about distinction between cusp forms and non-cusp forms.
Sorry, M is a property of the modular form, but doesn't it depend on gamma?
Right. So you can talk about the space of you can talk about the space of holomorphic modular forms for specific gamma of given weight. And then there's a definition. This is the elements of that space satisfy this property.
But doesn't it also, sorry, I guess I meant, doesn't it depend on the element of gamma?
No, sorry, this is for all, okay, this is for all elements of gamma, sorry, yeah. So for, I guess I should write it like that, but for all in gamma. So f is basically f is a section of the nth power of the canonical bundle over that surface. So it's some kind of nice holomorphic function on that surface, but doesn't have to have weight 0.
You'll be restricting your attention to holomorphic modular forms today?
I hope not, but yeah, I'm getting to non-holomorphic ones soon. So for just to give you an example, for SL2Z, the most famous one is the so-called modular discriminant, which is a cusp form. So it's the 24th power of the Dedekind eta. You can write it. So for if gamma is PSL2Z, there's an example with m equal to 6. So m equal to 6 is the smallest m for which these things exist for PSL2Z. And then we usually denote it as such, and it's q times 1 minus q squared to the power 24, or q is e to the 2 pi I z. Okay, and so if we denote the space of these holomorphic forms, so yeah, let's denote Sm gamma to be the vector space of holomorphic forms for gamma of weight 2m. Space of what I talked about above. For general gamma, then there is a nice formula. Oh, sorry. Then it turns out the dimension of this space is finite dimensional, which is really the main reason why people care about this, I think. So dimension of this space is finite, and it's actually determined by the topological data, so by the genus and the orders of elliptic points. For the special case of the hyperbolic triangle groups, I'm going to give you the formula because it's quite simple. So for this gamma ABC, it's this. So it's the floor function minus 2m plus 1 plus the Kronecker of m comma 1. So you can check for yourself that if you plug in SL2Z, so that's 2, 3, and infinity, then this formula gives you 0. and for all m smaller than 6, and then for m equals 6 it gives you 1, and then it nicely reproduces all the dimensionalities of the cusp forms for SL2Z. This can be derived using Riemann-Roch theorem, which is some kind of a generalization of the statement that the only holomorphic functions in the plane are constant. So in that case, the space is one-dimensional, but it can be finite dimensional for the modular forms. Okay, and the reason why these modular forms are interesting, in particular, is that for the arithmetic surfaces, they encode a lot of number theoretic information. In particular, you can use them to construct L functions, which I'll get to in a moment. But before doing that, I want to address what Eric has asked, which is that there is another rather natural but slightly more esoteric kind of automorphic forms, which are Laplace eigenfunctions. These are also sometimes called, usually called mass forms. And the way to think about them is that, so the holomorphic modular forms, they are basically functions on the surface which satisfy an extra differential equation, which is that the anti-holomorphic derivative annihilates them, so they're holomorphic. The Laplace eigenfunctions are similar, so they are also functions on the surface, and now they satisfy a slightly more complicated differential equation, which is the Laplace equation. So that's why they're analogous to the holomorphic modular forms. I'm going to denote them phi of y, so Laplace operator on the hyperbolic. So this is a different delta than this is the Laplace operator, which on the hyperbolic plane takes this form. And a mass cusp form, or mass form, is a function which satisfies the equation, the Laplace equation, where lambda is the eigenvalue. So you should think, and of course phi is invariant under gamma. So for all A, B, C, D in gamma. So you can think of the lambda as an analog of the weight of the modular form, and this becomes very transparent when you think representation theoretically. So there's like a nice representation theoretic view of all of this, which basically goes under the name of automorphic representations, where you can realize these things as kind of special vectors in infinite dimensional representations, living in, well, roughly speaking, in this space. I mean, it doesn't give full justice to the notion of automorphic representation, but it's the idea. So then both lambda and m for the holomorphic modular form have a meaning as labels of irreducible representations of PSL2R. But I won't have, I think, enough time to discuss this further. When the space is compact, then the spectrum is discrete, starting from 0. Then there's some spectral gap, and going off to infinity. And one of the lessons of this, of my kind of line of research over the last few years, is that there is a very close correspondence between, well, a close analogy between the spectra of these objects and the spectra of CFTs, which I'll hopefully get to relatively soon. Now, an important theorem about these spectra, which is actually valid even more generally beyond the hyperbolic setting, is a theorem of Weil. It's called the Weil law.
Question then.
Yeah.
Can you give some intuition why is it not worthwhile to consider further generalization where you consider some Laplacian-like operators acting on forms?
Well, I think the point is that essentially these operators which are already present are generate the algebra of differential operators which are invariant under PSL2R. So that's why these are special.
Although I guess in these Bonifaccio Hinterbichler works, they did look at such operators.
You mean in the Einstein setting?
Yeah.
Right. So in the Einstein setting, there is no PSL2R because the manifolds aren't necessarily hyperbolic. So it's natural to look at more general operators.
I guess there are higher order operators. right? You considered first and second order, but if you allowed yourself higher order, there would be more.
Well, I think the statement is that if they commute with the action of PSL2R on the upper half plane, then they can all be written as polynomials in Laplacian.
Because we know it.
Yeah, exactly. Okay, so the theorem of Weil, which will be important later on, but it's kind of different, in a different meaning than the Weil bound that I'll talk about at some point, is the statement that when you count the number of eigenvalues smaller than some cutoff, so the size of this set, then this goes like the area of the surface over 4 pi times capital lambda. So as capital lambda goes to infinity. So basically, at large lambda, the eigenvalues are linearly spaced in the lambda space, and the spacing is controlled by the area. So it's inversely proportional to the area of the surface. Now this is true actually even beyond the hyperbolic setting. Okay.
Sorry, so the fact it's linear, is it because we are in dimension 2 here?
That's right, yeah. In general dimension, this would be d over 2. All right, so far, okay, I haven't said much about the analogy to CFTs, but basically I suggested that there's an analogy between CFT spectra and the spectra of these operators for various lattices gamma. And I haven't told you yet what the 3-point functions are, so let me talk about those. Well, something that in physics we call 3-point functions, but in mathematics they usually call them triple products or trilinear periods. So just to set the stage, let me normalize. So let me define some inner products first. So let's say that okay, the inner product between two mass forms, so Laplace eigenfunctions, will from now on mean this following thing. So I'll normalize it by the area and integrate over the surface, so which is the same thing as integrating over the fundamental domain with this measure of phi1, phi2 bar. And you can work in a basis where the Laplace eigenfunctions. So this is an inner product on arbitrary functions on the surface, and now Laplace eigenfunctions can be chosen to be orthonormal and real. So let me choose that. So these are now Laplace eigenfunctions. You can do the similar thing on the space of holomorphic modular forms, but you should restrict them to have the same weight. So now let F1 and F2 be holomorphic modular forms of the same weight m. And then we can define the inner product in essentially the same way, except by the way, this is just the measure coming from the hyperbolic metric. The product of F1 and F2 bar is not quite modular invariant, but you can make it modular invariant by multiplying by y to the 2m. So the point is that this, if F1, F2 both transform as holomorphic modular forms for any gamma of weight m, 2m, sorry, yeah, there's weight 2m. So thank you. Yeah, there's this. It's somewhat more natural from the rep theory point of view to use m instead of 2m, but the weight is unanimously called 2m. And then we are going to work in a basis where the inner product is also diagonal. So well, all of the F are orthonormalized. Okay, so now given this, so this is kind of like choosing a basis of primary operators for your CFT.
So why don't you consider non-zero weights in a non-holomorphic case?
Well, all of those things arise by applying some lowering or raising operators to holomorphic forms or to Laplace eigenfunctions. So it's not obvious, but it's true that. Yeah. I mean, these are the. When you look at the G mod gamma and you decompose the L2 space, then the irreducibles correspond to these objects, and then the kind of things that you're asking about, they will correspond to non-lowest weight or non-lowest weight vectors or non-zero weight vectors in the principal series case. So yeah, it's not obvious, but it's true. This is the only interesting data that there is. Okay, so now finally I can almost state the main result of our work, which is that we are going to take. So let's take Fi Fj to be holomorphic modular forms of weight 2m. Then we can consider this this function, which is y to the 2m times Fi Fj bar, and let's assume that gamma is the space is compact for now, so no cusps. Then this is a genuine function on the surface because we are canceling the transformation of that by the transformation of y. You can check for yourself this is invariant from the definition I gave before, and you can expand this. You can then expand this in the basis of Laplace eigenfunctions. So the identity, the constant function, will contribute as conjecture delta. That's because of that normalization. And then there is an infinite sum. Sorry, I'm on k. Yeah, I'm on k. With some coefficients ci, jk times the Laplace eigenvalue. So this is just an expansion of a function in terms of the Laplace eigenbasis. And the ci, jk is what I call the 3-point functions. Right? So ci, jk is analogous to 3-point functions in a CFT. And just to make it super manifest, you can just multiply by phi k and integrate to write it as an integral of triple product. Okay. Okay. Yeah. Well, I guess I'm assuming that my fees are real, but oh yeah, I guess over there I put. Yeah. Yeah. That bar was unnecessary there. Let's say that phi are real.
What did you write? Cijk is 3 minus q?
Sorry, 3-point. My handwriting is 3-point function.
Oh, I see.
Right. So then the question that we addressed using conformal bootstrap is the size. So we are wondering what is the size of the Cijk as when we keep the Fi and Fj fixed and take k to infinity. Right, so in general, it's going to be some infinite sum, and we are wondering how suppressed is this infinite sum at large k. This, as it turns out, is closely related to some statements about L functions that I'll get to very soon. And what can you expect about the Cijk? Well, so this is a little bit like a Fourier series of a function, right? So and this function, because these are holomorphic, so in particular they are real analytic. And when you look at a Fourier series of a real analytic function, then the coefficients are exponentially suppressed. So you may expect that the Cijk is exponentially suppressed in the frequency. So frequency goes like square root of lambda. Right? That's the frequency of the Fourier mode. So you may expect that that Cijk is kind of suppressed should be of the order of e to the minus some number times square root of lambda. But actually, not much beyond this is known in general. But it's the beauty of hyperbolic surfaces that you can say much more about this problem.
Yeah, sorry, then.
Yeah.
So on the other types of 3-point functions, we could consider like 5.
That's right. Yeah. So yeah. I'll focus on these 3-point functions, but exactly as Sylvain is saying, you can maybe the most natural one is actually 5, because that one doesn't even involve multiplying by any measure. But essentially, for any 3 automorphic forms, there is a natural 3-point function. It's just that in our work, we focused on these ones. I think the method is more general. It can probably treat all of those cases eventually, but this turned out to be technically the simplest one. So I'll focus on it for now, from now on. So what did we actually prove?
You get compact.
Oh, right, yeah. So I forgot to say. Right. So if the manifold is non-compact, then there is also a contribution of continuous spectrum. And in general, this is more or less all that you get, just the continuous spectrum. But in the number theoretic cases, like SL2Z, there's an extra discrete spectrum on top of the continuous spectrum. And then you can ask the same question about those 3-point functions between cusp forms.
There's always a discrete spectrum on top of the continuous spectrum.
Not always. No, I think. Well, it's not really. It's an important open problem. I think. I think you expect that generically when you so there's always a discrete spectrum in the arithmetic cases. That follows from the trace formula. Mm-hmm. But the arithmetic cases are very special in the space of hyperbolic surfaces. And when you deform away from when you move a little bit away on the moduli space, or just look at some non-arithmetic case, then typically you expect that the discrete spectrum just resolves, becomes resonances in the continuum.
Are the arithmetic ones dense in the moduli space, or?
Actually, it's a good question. I believe they are discrete. Is it? Maybe some experts can correct me. Are the arithmetic? Well, they're certainly countable, the arithmetic ones, because they're countable in many number fields and etc. But I'm not sure if they can have accumulation points. I mean, they are certainly not dense because in the discrete part, so there's these, like I said, in the triangle groups, gamma ABC, only finitely many of them are arithmetic.
Oh, I see.
So you've got infinitely many of them which are not limit points of anything else, which are not arithmetic. But it's a good. I think they're probably discrete, but I'm not sure. Okay, so yeah, what did we prove in this paper from August? Adve, Bonifacio, Kravchuk, me, Pal, and Radcliffe and Rogelberg, is that when you look at the size of theCijk for any co-compact gamma, then it's bounded by, well, firstly there is an exponential, as expected, as I sketched before. And then there is a very precise power law, which is 2m minus a third, actually plus epsilon for any positive epsilon. And this is called the what was known before is the exponent and a power, which was a slightly weaker power. That was the work of Bernstein and Reznikov. So we essentially improved this power to, and this precise value of this power is what's referred as the Weil bound. Well, so Weil bound is the precise value of this power. It's something that mathematicians care about a lot. The precise value of this power, as hopefully will become clear as we go on. Well, the actual power that is expected is even better than that, which corresponds to the Lindelov hypothesis. And so this is slightly weaker than what the optimum is supposed to be, but it's somehow a natural barrier for various methods. And so some of the interesting thing is that besides kind of inherent interest in spectra of hyperbolic surfaces, this result actually has a lot of relevance for modern number theory.
Can you motivate the exponent of e to the minus pi? Because if you motivated this exponential behavior from the real analytic, but in that case it comes like from the nearest singularity in the complex plane. So what does it mean in case of surface?
So I'm not quite sure, but I think this pi is very much related to the surface being hyperbolic. Somehow the hyperbolic surfaces are things that kind of can be analytically continued by an angle pi or some like it's very vague. But I don't have a good intuition. If anybody has a better intuition for why it's exactly pi here and not something else, I mean, it will naturally come from the L function language, where there is a pi. But I don't have a good analytic intuition. Right. So this result, like I said, corresponds to a particular nice bound on certain L functions. So it's finally time that I stop saying L function and actually tell you what they are. And there's some. Oh, okay, maybe I'll say this a bit later. Okay, so that's part 2. I can already see that I'll probably have to compromise on some of the material later. L functions. So L functions, most kind of prosaically, are some entire or meromorphic functions in a complex plane. So typically, the variable in complex plane that they depend on is denoted S. And the definition is a bit unilluminating if you haven't studied them for a long time, I guess. But they arise very naturally in number theory, and they kind of combine the right minimal set of ingredients to lead to very rigid, kind of magical number theoretic objects which encode a lot of number theoretic information. So it's probably best to start by an example, which is the first L function that was discovered, which is the Riemann zeta. That can be first defined through something called a Dirichlet series. So it's a sum over all positive integers of 1 over n to the s. This, of course, converges only when the real part of s is greater than 1, but there is a unique analytic continuation everywhere in s except for a simple pole at 1. And the most important properties, or the defining properties are of this function are the following two. So it has an Euler product, which is a product formula over primes. So you can write, whenever I will write p, it means prime. So here it's a product over all primes starting from 2 of 1 minus p to the minus s to the minus 1. So the fact that this is equal to that is equivalent to the fact that any positive integer can be uniquely factorized into pairs of primes. And the second property is a functional equation. So to state the functional equation, let's first define this function of s, which is kind of a modified gamma. I'll call it gamma tilde, which is p to the minus s over 2, gamma s over 2. And then if we write, if we define this kind of completed L function lambda s as the product of Riemann zeta and this function, then this function is invariant under s goes to 1 minus s. Right, so the Riemann zeta in a complex plane is not quite invariant under s goes to 1 minus s, but if we multiply Riemann zeta by this nice function, then we get something which is invariant. And this can be proven by writing zeta as essentially as a Mellin transform of a Jacobi theta function. Now why is this function relevant for number theory? Well, it's because of the Euler product. So, because the function can be written as a product over primes, its analytic properties encode various statements about primes. So, the first statement that is almost immediate is if you take the limit of s going to 1, then there is a pole because the harmonic series diverges. And here in the Euler product, nothing really goes wrong unless you have infinitely many primes. So if there are finitely many primes, then this would be finite. So this already shows you that there have to be infinitely many primes by taking s goes the limit of s going to 1. It's of course kind of a silly application, but probably the first application of the Riemann zeta that was the reason why Riemann was looking at it was counting the number of primes less than a certain magnitude. So that's number of primes less than x. And what has eventually been proven is that this goes like x over log x using the Riemann zeta function. And this follows more or less directly from the statement that the Riemann zeta has no zeros on this line 1 plus it. Right, so an analytic property of the zeta function immediately leads to a statement about primes, thanks to the Euler product. And there are various conjectures about the zeta function which imply various number theoretic properties. So the most famous one is the Riemann hypothesis. According to which, if you look at now this lambda s, so its only zeros are when the real part of s is 1/2. And if this were true, then this would imply a kind of optimal error term, optimal size of the error for this. So this is called the prime number theorem, but I won't write it because I think I write kind of slowly. So yeah, so the optimal error term in a prime number theorem is equivalent to the Riemann hypothesis. Well, now there's a slightly weaker hypothesis, which is also this is unproven. This is also unproven, the Lindelov hypothesis, which asks about the size of the zeta function on this critical line. So there's this line 1/2 plus it for t real. And this hypothesis says that this thing is bounded by arbitrarily small positive power of t. So for all positive t, there's an upper bound like that. So it can grow, but it can grow like a logarithm, but it cannot grow like a square root of t or anything in the power of t. This actually follows from, if you could prove Riemann hypothesis, you would prove Lindelov hypothesis, but it's weaker. So recently it has served as a proxy for Riemann hypothesis. So kind of how close can you get to proving Lindelov hypothesis brings you a little bit closer to Riemann hypothesis, but still, this is still like infinitely further than the Lindelov hypothesis probably. But nice thing is that here you can kind of nicely measure how close you are to proving it by seeing how good the exponent is. And this exponent will actually be related to that exponent in the CIJK bound that we proved with Stradip and friends. I mean, not for the zeta, but for other L functions. So, and what is maybe I can write it here. Yeah, so what is known about the Lindelov hypothesis? There's a convexity bound which just follows, which was actually proven by Lindelov. So Lindelov didn't prove Lindelov hypothesis, but he proved the convexity bound, and that just follows from the functional equation and analyzes the properties of zeta, which is that this power is at most a quarter. So 1/4 is the same as convexity. Then finally, I can explain what while is. So any improvement of this 1/4 below is called subconvexity. So if you have heard about the subconvexity problem, this is, maybe you don't know what it is, this is what it is. So subconvexity means that that we have a 1/2 plus IT, and we can bound it by t to the alpha, where alpha is less than 1/4. And now I can finally explain what while means in the title of our paper. While is just such a bound where alpha is 1/6, or maybe 1/6 plus epsilon. So it's 1/3 of the way from 1/4 to what's supposed to be optimal. So optimal is supposed to be 0. So going from 1/4 to 1/6 is like you're 33% of the way to the optimal result. And Bernstein-Reznikov were half of that. So they were, I guess, 1/6 of the way to Lindelof. Funnily enough, the while bound was not proven by Weil, but by Harder and Littlewood, although they didn't write it down, as far as I know. So this for the Riemann zeta, the state of this was the state of the art for a while, but actually the state of the art right now for Riemann zeta is that alpha is better than Weil just by a little bit. So it's 1/6 minus 1/84. And that's due to Bourgain, who used to be a professor here from 2017. So it's the area of current research improving this exponent towards Lindelof. Okay, well, I think it's probably a good time to take a break now, because we are about 1 hour in. So let's meet again in 5 minutes. All right, so that was the Riemann zeta and its associated conjectures. And it turns out that there is a very natural, a kind of rigid generalization of Riemann zeta, and that's what L functions are. L functions are kind of very natural generalization of it, even though it may not seem very natural, as I will when I write it. But the right way to understand why L functions are the way they are is actually using representation theory of this group. So there's a big group which is GL2 over the Adels, which is something that kind of factors over primes in the right way, and it leads by basically doing some integrals over this group. You're very naturally led to this notion of L function, but I won't be able to explain that. Although it is related to the Bootstrap in the sense that it is the same role of representation theory that we also see in the Bootstrap. But for the purpose of this lecture, the L functions will be just kind of defined in an ad hoc way by hand. So L function firstly is a Dirichlet series that looks like that. So it's a sum over 1 over n to the s, but now instead of 1 with some coefficients, complex coefficients an. But they're not arbitrary coefficients. They are subject to many constraints. The first constraint is that there should be an Euler product. So this is some version of the fact that these coefficients are multiplicative, that the a at n times m should be related to the product of a n times am. And the way to write it is that you can still factor this into as a product over primes. But now this factor at prime p doesn't have to be so simple, but instead it's an inverse of a degree d polynomial in the p to the minus s. And this d is called the degree of the L function. And it's the same d as the d in the representation theoretic point of view on L functions. And this factor then at prime p factors into d terms. And this alpha is some kind of local data, local because it sits at this prime p. in the representation theoretic view, these alphas are labels of infinite dimensional representations of GLD over the p-adic completion of Q. And so that's the Euler product. And then there is a functional equation, which is also a property of the general L function. Where now, to state it, we need to define an analog of LP, but L infinity. So in the same way that these P's are associated to the p-adic completions of Q, this is associated to the real numbers, which is the remaining completion of Q. And this is just a product so gamma tilde is the same gamma tilde that we had before for the Riemann zeta. There is again d of them, so the same d here and here. And now this mu j is also a part of the local data, but now it literally labels infinite dimensional representations of GLD over reals instead of GLD over Q. So there's a very nice kind of representative theoretic way of stating all of this. But okay, but now what's the point? The point is that if you define this completed L function as the product of the infinite S and these LPs, then this satisfies the functional equation with some number epsilon, some number n, and okay, I think something like that. So, and this is the remaining data that you need to specify this L function. So, okay, I won't really. This is called the root number. Oh, so it's S. Oh, where?
Like it relates lambda S with lambda at 1 minus S? Or
Yeah, in this convention, it's 1 minus S.
But
I mean, there are different conventions.
for d bigger than 2, isn't it d over 2?
Depends on the, I mean, in this convention that I'm setting things up, I mean, I guess it depends. You could get your convention by shifting the S here by something. But I think this is correct. I took this definition from Michel's review of subconvexity, so I'm pretty sure he didn't make that mistake.
No, but we're just saying it's true for general D.
Yeah. This is the definition for general D.
So lambda is not meromorphic. Why do you have to write lambda of 1 minus S bar bar?
Oh, it's so this is holomorphic because there's a bar on S, but in bar over the whole thing. This is again holomorphic, but it can flip some. It can act like some complex conjugation on this local data, for example. So it relays the lambda to the dual lambda somehow. Okay, and n is called the conductor, or the finite conductor. Okay, well, those are just some names. Huh? Oh, epsilon is called the root number, but you don't have to remember. It's just
Also, for some finite number of polynomials of low order, maybe we should say it's alpha is equal to 0. Yeah, alpha could be 0. Yeah,
alpha could be 0. Yeah, alpha could be 0. It's yeah.
What is n?
Because if it's not normal, because alpha should have norm 1 maybe, yeah? In this case.
Right. For when it's a principal series, then there's a conjecture from Ramanujan that the norm of alpha is 1. But okay, I guess.
Then for some few exceptions, P divided conductor will be less terms.
Yeah, that's right. So the actual degree of this polynomial can be less than d for some finite number of p's, but then they just correspond to special values of alpha. So I think this definition is still kind of general enough. Yeah, there was alpha.
For general L functions, which don't need to have all these properties, have people studied spectral questions for the associated surfaces?
for the cases where you can associate actual L functions to surfaces, they do have all of these properties. So those correspond to the arithmetic surfaces, and in that case, there is this whole representation theory machinery, and you can associate such L functions to those.
But for the other cases,
For the non-arithmetic surfaces, I don't, well, these kinds of L functions do not play a role, as far as I know. Okay, so then the kind of the natural setting for L function is the so-called Langlands program, and an important part of Langlands program is the statement that somehow all L functions of all objects that satisfy these properties come from automorphic forms, and that's why there is this relation. And we'll see some examples of how L functions arise from automorphic forms very soon. The conjectures that are expected to be true for Riemann zeta function are still expected to be true for the general L function. So the Riemann hypothesis is still expected to hold, even though it's not proven in any of these cases. And Lindelof is also supposed to hold. But in this more general setting, there is a kind of a nice generalization of Lindelof, because in the original Lindelof for Riemann zeta, we were just varying S. But now we have a large class of L functions, which are basically parameterized by this data, the alpha and the mu. And we can vary those data as well. So we can say fix D. And we can ask, can we put some bounds on the values of L functions, fix D for arbitrary alpha and mu, which satisfy these properties. And there is a corresponding Lindelof conjecture for that setup. So one first defines something like measure of the complexity of the L function, which is called the analytic conductor, which is this number n times a product of d things, so 1 plus mu j plus it. So sorry, this t now refers to the, so we are evaluating L at 1 plus it. And then there's a conjecture that all the L functions satisfy Lindelof. Sorry?
Sorry. I think some people complain that it's a bit small, so it's hard to read.
No, here it's very nice.
Okay. Sorry. Okay, so the conjecture is that this L is bounded by an arbitrarily small positive power of C, kind of for all L of fixed D. And a positive epsilon. And again, there is a convexity bound, which can be proven essentially from the functional equation, or something called the approximate functional equation, which is basically the functional equation, which is that the function is bounded by the c to the 1/4. And the same names still apply also in this more general case. So Weil would be c to the 1/6. And what we proved is an example, is a special case of this bound with the Weil exponent for a certain infinite class of L functions. How it's related to, well, how the Cij(k)s are related to L functions is what I'll explain now. Yeah. Okay, so. Okay, I think at this rate I won't say much about the Bootstrap, but at least I'll review all the ingredients so that you can understand. You can start reading the paper. Okay, so why is there a connection between L functions and modular and automorphic forms? Well, the rough idea is that modular forms satisfy some transformation property under, under something like z goes to 1 over z, or under some gamma, and this, by doing a Mellin transform, applies the functional equation. So if you Mellin basically, if you do some integral transform of an automorphic form, in the simplest case is the Mellin transform, then the resulting Mellin transform will satisfy this reflection under s goes to 1 minus s as a consequence of modularity of the thing that you're transforming. Okay, well. Okay, so the result that we proved for the 3-point function is related to so-called triple product L functions, which are L functions of degree 8. And let me just kind of yes.
What is mu j there?
Mu j's are the same. I just erased it. So mu j's are the quantities which enter into the gamma factors in the functional equation. So if you want to write a functional equation for the L function, you need to multiply it by some gamma factors, and those mu's enter into those gamma factors. So.
Do they have some relative properties?
I think they're probably real in this. Yeah, I'm not quite sure in general. Yeah.
And if you restrict it to the zeta function, it keeps you within the hypothesis.
Oh right, yeah. So for the zeta function, c is just t basically, because mu is 0. Yeah, there's only one mu and it's 0, and then therefore c is just t. For a degree, so if you vary t only, for degree d L function, the c goes like t to the d. So the Weil bound would be like d over 6.
So what is not clear if there is some uniformity in the constant as you vary L.
That's what's implied. So the constant should only depend on d and epsilon. Yeah. But it's very far from being proven in this generality. For d equal 2, it is proven due to Michel and Venkatesh, and then various partial results are true for general d. Especially recently, Paul Nelson proved this for general d. Proved subconvexity for general d. Sorry, Michel and Venkatesh proved subconvexity for d equal 2 with no extra, completely uniformly. And Nelson proved it for general d as you vary t, but you don't necessarily vary the other parameters. I mean, that's among many other things that Nelson and other people have proved, but those are just like snippets of recent results. I mean, there's a rather active area over the last, say, 20 years, maybe even more. So how do we start from a module of automorphic forms and build L functions? Well, if we are in the setting of, say, SL2Z again, for simplicity, then you can take a holomorphic modular form of weight 2m and write its, so suppose it's a cos form, so it has the Fourier expansion. an exp 2 pi I and z. And then you can define, in this case, the alpha in the notation for the L function that I had before would be inverses of each other, and they. So let me just call this alpha in that case. So alpha p plus alpha p inverse right. So the statement is that if you take a holomorphic modular form, which is in addition an eigenfunction of all the Hecke operators. So okay, I wanted to explain this, but I don't think I have time. So it should be an Hecke eigenform. Basically, this Hecke eigenform property guarantees the multiplicativity for the Euler product. And if you define the alphas from A, so A is something that you can read off from the modular form, then you can define the alpha in this way. So there's a unique solution up to exchanging. And then you plug it into the definition of an L function that I get before for d equal to 2. Then there's a theorem that this is actually an L function which satisfies the functional equation. And you can prove the functional equation by invoking the symmetry of f of z goes to is the same as f of 1 minus z, somehow. This is the so-called standard L function for this holomorphic modular form. You can do the same thing for you can do the same thing for a Hecke for a Hecke mass eigenform, so a Laplace eigenfunction. In that case, the m is 0, but you still get a degree 2, so d equal to 2 L function out of it. But now the nice thing is that you can kind of use this basic data to build more complicated higher degree L functions. And it's not obvious that those will satisfy functional equation, but people have proved it in some cases. And this is a reflection of something called Langlands functoriality. It's a part of the Langlands conjectures. Essentially, you can from finite dimensional representations of GL2 or GLG in general, you can build more complicated higher degree L functions, and the degree is the dimensionality of this representation P. Higher degree. And the ones which are the examples of this functoriality idea that are relevant for the 3-point functionsCijk is the symmetric square of GO2. So that's a 3-dimensional representation. And the so the symmetric square, it's thought of as a representation of GO2 it's a homomorphism from GL2 to GL3. It's a homomorphism from GL2 to some 3-dimensional vector space. And it leads to, so starting from F, you can build a degree 3 L function whose alphas, so basically the local factor, we can talk about the degree 3 L function. So the symmetric squared of F. So F is still a holomorphic modular form of some weight 2m for SO2z. And this factor P is now degree 3 and looks like 1 minus the alpha squared over P to the S, then P to the S, and 1 minus alpha P minus 2 over P to the S. So you can kind of see how the symmetry, if alpha and 1 over alpha are the weights under the fundamental of GL2, then the weights under the symmetric square of GL2 is going to be alpha squared 1 and alpha minus to the minus 2. And then you can also, so this is one important formula which will play a role. And another one is the tri-fundamental for GL2. So for GL2, GL2, GL2. The tri-fundamental is a homomorphism of this to GL8. And the corresponding triple product L function, which is really the main player in the connection. Okay, so now let's go to the setting where we have some Fi and Fj be the holomorphic of weight 2m, and phi k is a mass form, so it's a Laplace eigenfunction. And let's suppose that they have Fourier coefficients. So the Fourier coefficients of f will be a. Sorry, q to the n. For coefficients of fj will be called b. And those for phi will be called c. So here it's not quite q, but it's some Bessel function. If you've seen mass transforms, then you know what this is. But it doesn't. Basically, they are just the coefficients in the Fourier expansion of the three objects. Then from these numbers, we can build a degree 8 function that's okay. So first again, let's introduce these alphas. Now, in this case, it's known that the alphas have a unit modulus. That's a theorem of Dalimil for the holomorphic case. And then okay, so this is how you define the alphas, and then for each of these there could be this degree 2 standard L function. But now let's build the degree 8 L function, where the local factor has 8 terms. So sigma 1, sigma 2. So is it? I was told to write bigger. Sigma 1, sigma 2, sigma 3 is plus or minus 1, and we put 1 minus alpha p to the sigma 1, beta p to the sigma 2, and gamma p to the sigma 3 over p to the s, all the thing to the minus 1. So this is degree 8 because there are 8, this product has 8 terms. And I'm not going to write down what the L infinity is, but you can ask me later. But for each of these, both for the symmetric square, degree 3, and for this triple product, degree 8, there is a corresponding product of gamma factors, the correct number of gamma factors, which guarantees that this L function satisfies the functional equation. But finally, okay, so I should have good proper notation to be consistent with the previous notation. This should be the triple product. So f1 or fi, fj, phi k, s. And finally, so what's the connection between 3-point functions and L functions is a content of a formula that in this form was derived by Watson and Ichino. Theorem of Watson. Well, there are two separate papers. I guess there were some precursors before, but those are the main ones. That now let's do for SL2Z. That if we look at so let's recall thatCijk is 1 over the volume, the integral is the 3-point function, and Watson and Ichino gave a formula for c squared. So look, here I'm assuming that they are normalized, so let's do fi. So if we normalize everything, then there's a formula forCijk squared in terms of these L functions that I defined before. I think for sorry, I think this is probably the volume of over 8. And there's a beautiful formula that we take the completed triple product L function of fi, fj, phi k, and evaluate it at 1/2, so exactly the middle of that critical strip, and then we normalize it by the symmetric square L functions for the 3 evaluated at 1. Okay. Yeah, so I mean, if you just look at it, it's completely crazy, right? Because this is some kind of, well, they are both some highly nonlinear functions of the Fourier coefficients, but they are very different nonlinear functions of the Fourier coefficients. And like this, for example, also requires analytical continuing. That that Euler product is only going to make sense when s is greater than 1. But the statement is if you analytically continue to 1/2 and evaluated this ratio, then you're going to get the integral of a trivial product of automorphic form squared. Here? No, it's. I mean, you should think the L function is kind of defined in terms of the spectral data. Yeah, it's just the representation. Yeah, and actually, the way this is proven, an important ingredient of it is the statement that in the CFT we know as the uniqueness of 3-point functions. That kind of 3-point functions are. 3-point function, a 1D CFT, so for SL2 are unique up to overall rescaling, and the same is true over the p-adics. So that's how you kind of fix the structure of this as an Euler product, and then you somehow need to get the overall coefficient, which I don't know how Watson and Ichino did it, but it's quite remarkable. So now. Now, if we have a bound, an upper bound on theCijk, as k goes to infinity.
Sorry. I don't believe it because I think you should put bar because if you replace I and j, isn'tCijk replaced by complex conjectures?
Sorry. Yeah, I should have put absolute value. I mean, will that resolve your complaint? Yeah, sorry. SoCijk is not in general real. Okay, there we go. Let's see. Yeah, so just to kind of maybe say once again what formula says. The formula says that if you take 3 homomorphic modular forms, you can do if you take these fi, fj, phi k, you can do two very different things, right? You can either just take their product and integrate, you get aCijk. It's kind of simple. You can do a very different thing, which is to first expand them in the Fourier decomposition, read out the coefficients, then calculate these alphas, betas, and gammas out of them, then plug it into the formula for the triple product L function, and then take those things, evaluate them at 1/2 and 1, 1, 1, and magically those two things are the same.
Wouldn't the formula be the same for to replace fi, fj by other mass waveforms?
Yes, but this factor will change. But this is more general. So for any, the generality is for 3 automorphic representations of GL2.
Is there an arithmeticity assumption there?
Oh yeah, yes. So the way I stated it is for more or less for SL2Z. I didn't explain to you. So I didn't explain a very important thing, which is why if you have an arithmetic surface, how do you get these alphas and betas? So that's not obvious because there is no cusp, so there's no Fourier expansion. But these alphas and betas, they still come as eigenvalues of Hecke operators. So you can do that, but certainly this formula is only true in the arithmetic case. Otherwise, there is no connection to L function that I'm aware of. So somehow the bound onCijk that we proved is more general because it's proved it doesn't rely on arithmeticity. But in the arithmetic case, it says something about L functions. So what does it say? This bound of A, B, K, M, P, R, R, which is just remind you that theCijk squared is upper bounded by e to the Okay, now let me write it in a slightly different way. So ptk, tk to the 4m minus 2/3. Sorry, because I'm writing too small. So here I'm just changing a notation a little bit. Instead of using the eigenvalue, I'm writing the eigenvalue as 1/4 plus tk to the squared, because this is the more natural parameter. Then this bound implies a bound on this triple product L function evaluated at 1/2, which is tk to the 2/3, I suppose. Well, it's the conductor to the 1/6, and the conductor is, sorry, I just, oh, let me be more general, so be more pedagogical. So a subconvex bound would look as follows. Right, so you can measure how far you're to Lindelof by sigma, where sigma equals 0 means convexity, and sigma equals 1 is Lindelof. In this case, the conductor for this L function, so if we fix everything except for lambda k, the conductor goes like tk to the 8, because it's a degree 8 L function. So then what we proved is the Weil bound, so that corresponds to sigma is 1/3 of the way. So then I guess we can plug it in. For some reason I didn't put it in my notes, but sigma, this is 2/3. This is 1/6. So 8/6, which is 4/3. Okay. So what we proved is Weil, which is this is the same thing as t to the 4/3. So not quite for it to be Lindelof, this would have to be 0, but it's better than the previous state of the art.
Is it a big limitation from the point of view of applications that you can only prove this bounds for the L functions evaluated at 1/2? Because I thought that in the general bound you're supposed to prove it for any t. Yeah. For any value on the imaginary axis. Right. So 1/2 plus it.
It's not really a limitation. It turns out that you can. It's basically you're pointing out there's some kind of asymmetry between the different parameters. That the t is one parameter, and then there is these representation theoretic parameters. These, but you can make the t into a representation theoretic parameter by kind of tensoring with a one-dimensional character. So then you can kind of move yourself along this critical axis by multiplying by the character of GL1, which is just the number to the power it. So then everything is very democratic between the different parameters. But we only proved that we only have access to this one at 1/2. But there is a way to kind of formulate everything more symmetrically. The general subconvexity story. I mean, our story is just.
This result implies the more general one?
No. If you could prove this result for more general triplets of forms, then yes. But
have there been Weil strength bounds in the T aspect for these guys proven before?
Yes. So that's exactly a good question. That's what I wanted to say now. So what was known before our paper? So for the setting of general gamma. For general gamma, Bernstein-Reznikov in 2010 proved that sigma is at least 1/6, so that's halfway towards Weil. And then for gamma SL2Z, result of Blomer, Jana, and Nelson from a few years ago is the while bound. So sigma the 1/3. So you may ask, when is this result that we have for L functions new? And it's for all other cases which are arithmetic, but which are not SL2Z. So somehow this is most of them, because it turns out that most arithmetic groups are not SL2Z. This can probably be generalized to congruent subgroups. So basically, for all the non-compact cases, arithmetic non-compact cases, it's been known, but it was this method. Their method doesn't generalize to the compact cases. So the compact case is harder in this case, at least from the point of this method. And then our result is new also for the L functions. Okay, so I have about 20 minutes to explain how this is related to the Bootstrap. But maybe first, are there any questions about what I've said so far?
The Bootstrap is used to prove the bound on the CIJK, or to make the connection between the connection was known?
On the CI, yeah, the connection to L function was known due to Watson,
Yes, okay.
and the Bootstrap doesn't use any number theory. The Bootstrap is it's kind of nice that it's general for any surface. And you can ask, do we expect Lindelof for general surface? Maybe yes, even if it's not arithmetic.
For these kinds of L functions, have there been efforts to get a Weil strength bound or any other bound from computing moments, like Steve Brown did for the 12th moment of Riemann zeta?
Yeah, right. I think that's right. So I don't know much about it, but what I know, I think Lindelof is definitely equivalent to some statement about moments, about the growth of moments. I'm not sure what the weaker versions of Lindelof, so subconvexity would be in terms of moments, but I can, yeah, maybe you know actually more about this than me. I don't know. There could be some such results. Yeah. All right, so just a sort of sketch of the method. Firstly, you can focus on, without loss of generality, you can focus on Fi being Fj being the same, of the same weight, m to m. And let's just call it F. And then let's just denote Cijk. In that case, let's just denote it Ck, because the dependence on Ij is not interesting or not important for us. And then the idea is to use associativity of multiplication. So if you take product of three automorphic forms, you can use this OPE, or this spectral decomposition, in two different ways. And it's a constraint on both on the spectrum and on these Cs. And this can be most sort of nicely expressed by looking at a 4-point function. So you can kind of define a 4-point function, or just in general, let's define a correlation function to be just this integral, where we make sure that whatever we are integrating has the correct weight. Well, in this case, I guess weight 0. And then we can, for example, look at just FF bar. And I'm dropping, by the way, the y. So there's always some power of y which needs to be inserted to make it make sense. And you can write this. You can either use the spectral decomposition like that, in which case it gives you the sum of c. So in this case, ck is real if fi is the same as fj. I'll just write as ck squared. So it gives you sum of ck squared. Or you can put the brackets like that, so you can kind of expand this product and this product, in which case it gives you ck squared. So it's not very interesting in this case, it just gives you a trivial equation. But you can get non-trivial equation if you insert some covariant derivatives. So for example, already if you insert a holomorphic covariant derivative here, you need to make sure that there is the same number of holomorphic ones and anti-holomorphic ones. Then, well, if you express it one way, you get sort of ck squared times 2n minus lambda k ck squared. So that's if you do the S channel. But if you do the T channel, you get lambda k. So this was kind of the point of view that Bonifacio and Hinterbichler introduced in their work, inserting these covariant derivatives and just using basically the fact that the commutative covariant derivative is the Riemann curvature, which is of course constant on hyperbolic manifolds. So it's well, it gives you it measures the weight, twice the weight of your form. Right? If you actually the curvature on a weight m form, you need to use it m times. So.
Are there two factors of ck squared in the equation there?
Sorry, thanks. Yeah. Good. Right, so this equation would imply that the sum over ck squared times lambda k minus m is 0, right? So it already tells you something non-trivial, that there kind of has to be as much weight in the ck's, where lambda is less than m, there is when lambda is greater than m. It also implies a simple bound on ck squared, which is that it has to go like 1 over lambda to the k. Right? For this to converge, ck squared better be less than 1 over lambda k. So it's quite far away from being exponential as we need, but you can by basically inserting more and more derivatives, you can get higher powers of lambda, and eventually you can get an infinite set of equations which constrain ck squared in this way. And you can hope that the total set of these equations implies the Weil bound, or the bound that you need. Now, at this point, it's very. No. From what I said, you cannot hope that. Yeah, but it's. I'll try. At the end, I'll try to say why the Weil bound is the barrier. But from now, from what I said, it's not.
You might as well hope for Lindelof.
You may hope for Lindelof, and maybe if you use mixed correlators, you can try to get Lindelof.
No, but I'm confused how you can hope for anything like Lindelof, because you're not using any arithmeticity here yet.
Well, Lindelof is probably also true non-arithmetically for the CIJK. So Lindelof is not super number theoretic. It's just some kind of.
I understand. You just said you have to have L functions. You have to have a functional equation. So this already becomes arithmetic. So what does it mean to have non-arithmetic?
I think you still have a functional equation. Just the L opposite. You might not have an
I think the confusion comes from the fact that the relation between the CIJKs and the L function was stated to be present in the arithmetic case. So why you would hope for something for the L function without arithmeticity was, I think.
No. So there's a right. Yeah. Maybe I should clarify something. So the CIJK. Let's stay in a compact case. The CIJK always makes sense, and you can ask what is the best possible bound on it, and that's a question. Then, when the manifold is arithmetic, you can relate CIJK squared to L functions, and they can be defined also in a compact case. When the manifold is arithmetic, and then you can ask what is the expectation for the size of CIJK squared from Lindelof for that L function, and that gives you some power. And then you may wonder whether the same analogous result will also be true in the non-arithmetic case when there is no L function. Okay. And I think that's probably what's expected, but I'm not quite sure. Okay.
This is expected when all these L functions business is the red herring.
No, it's expected because of the connection to L functions. I mean, nobody had before, without Watson, nobody would have any idea what the precise power should be. Even the inversion for the exponent, e to the minus.
Well, I'm surprised you say that, because you said L functions are very special. On the other hand, the exponent is the same whether you have L function or not. Well, then they're not special. Then just forget about L functions. Think in terms of the CIJK.
Sure. I could have totally given a talk without mentioning L functions ever, just talking about a bound on CIJK squared. But then somebody could ask, well, why do you even care about CIJK squared? And well, one reason, of course, it's a sociological question, right? So. Okay. Yeah. Well, I think but that's maybe hard to convince people that's good if I don't mention the L. So the L functions, there's a nice number theoretic application, which is actually something that many number theorists care about a lot.
But yeah, I mean, I agree with your comment.
Oh, sorry, maybe I misunderstood. You told us if you iterate, take high derivatives, you get more and more equations.
Yeah, if you can insert higher derivatives in any of the 4 vectors on any of the 4 f's, and you get more.
In GCS's case, you get some more complicated ways.
You get polynomials in lambda and m in this case. But just
Some standard polynomials.
The polynomials, I don't think they're so important because I'm about to write down a compact generating function for all of them. Okay. So now, if you take the representation theoretic viewpoint, which I kind of suppressed today, then you can derive a nice formula for nice generating function for all the equations. So basically, you can. It turns out that all of those equations are equivalent to the following statement. You can define a 4-point function depending on the cross ratio chi, which is a sum from 0 to infinity of ck squared times a conformal block of chi. And this conformal block has a very simple formula. It's a hypergeometric 2f1 delta 1 minus delta 1 and chi. So for the experts, this is the conformal partial wave in 1D CFT. It's a sum of a block and its shadow in some frame. And then the interchange, so basically the associativity is equivalent to switching 2 and 3. You can think of the cross ratio as being x1 minus x3, x2 minus x4 over x1 minus x2. So it's just a Slav permutation of the usual definition. And then the associativity is the same thing as x2 switching x2 and x4, I think, which should be okay, I'm not sure. Well, let's just say associativity is the same as switching chi and chi over chi minus 1. 1, 2, 3. Yeah. Oh, okay. Good. Then I think what I was going to write is correct. So this is the same thing as switching. Thanks. You have resolved my confusion why I erased it. And then associativity is just a statement. This function is symmetric under that permutation. So you can just of course expand this in the same way. Oh, sorry, I'm completely missing the weight here. There is a dependence on m, which is important, and it's chi to the 2m in the conformal block. So you can reproduce, for example, this identity by expanding around chi equals 0. So this is true. Okay, this is true for any chi which is not on the branch cut of the hypergeometric function, and series around chi equals 0 reproduces everything that you would get from inserting the covariant derivatives. But this equation is kind of true holomorphically everywhere in this complex region. And in particular, to prove the while bound, we need to go far away from chi equals 0. So we need to take infinite linear combinations of the kind of equations that you would get by inserting covariant derivatives. But it's actually quite simple why you should expect subconvex or convexity. Okay, maybe for people who are not experts on the conformal bootstrap. Right, so there's an expansion of this function, and there is a symmetry of the function, but the expansion doesn't respect that symmetry. So the symmetry is a non-trivial the symmetry is a non-trivial constraint on these coefficients, on the C case and the T case, so on the spectrum and the structure constants. I should say this was proved in the paper with Kravchuk and Sredip from 21. And the reason these hypergeometrics appear is that they are solutions of some second-order differential equations, which secretly is the Casimir of SL2. And the reason that SL2 appears is, of course, because it's we are working in the hyperbolic plane. Okay, so one thing that you can do now is to start exploring this equation in the complex chi plane. There's a branch cut. This is chi. There is 0. Now, around 0 is just polynomials in lambda, like before. And you can, for example, ask what happens when you go far away from 0 at some angle theta. Well, when you do that, you will see that so if we go to 1/2 plus it, if you go at angle theta, then the conformal block at fixed t, at fixed r and theta and large r goes. I think I'm just missing something. At fixed r and theta at large t. So we are wondering what happens at large t. That's the whole point, right? The conformal block blows up exponentially with a rate pi minus theta times t. So because those equations, we prove they converge, those expansions, it better be that the ck squared decays faster than this exponential factor. Right, so already from just by looking at the conformal block at angle theta, when you make the theta arbitrarily small, you see the correct exponential decay. So this gives you the right exponential decay.
What was phases during the decomposition?
Well, yeah, but just from you want this to converge. I mean, what we prove is that it converges absolutely. So the phases. Okay, so just from convergence, you already get the right exponent. So it's not so crazy that you may hope for more and even get the right power in front. And then, well, let's just to get the right power, you need to wonder what happens when chi goes to 1. So when chi goes to 1, the expansion is not, the individual conformal blocks are not particularly divergent. They go like a logarithm. But from the symmetry, you know that actually g of chi needs to have a power law singularity. So this is the identity, the trivial representation, the constant function in the cross channel, plus order 1. So the sum of these conformal blocks is more strongly convergent than each individual conformal blocks, and you can wonder what kind of ck, what behavior at large k do we need to reproduce this power? And it turns out this is exactly Lindelof. So the power that you would get from Lindelof. So remember, Lindelof is that ck is ck squared is e to the minus pi tk times tk to the 4 minus 2. So I'm kind of assuming Lindelof with 0 epsilon. So if you just take this function of t, then we have the Weil law. So not the Weil bound, but the Weil law, meaning that the density in lambda space of the eigenvalues is constant. So density in t space goes linearly in t. So basically you want to evaluate the integral over t. The density is t. Then Lindelof gives you e to the minus pi t and t to the 4 and minus 2 times the conformal block, 1/2 plus it. Okay. Then this is exactly the right power law to reproduce the power law divergence expected from the identity in the cross channel. So that seems promising. But now you need to take this intuition and make it into a rigorous bound on CKs, which is not so easy. But luckily, our collaboration had some experts on those kind of problems. But basically, the idea to prove it is to construct some suitable functionals, which so to prove while bound, one needs to construct some suitable functionals. Similar functionals appear in Tauberian, various Tauberian stories in Conformal Bootstrap functionals.
So is the difference between average sort of Tauberian-like result and point-wise bound? Is this why is this argument not?
Exactly. Yeah. So exactly. So this kind of argument naturally leads to the convexity. So the convexity bound is the same as Lindelof on average over the long interval all the way up to t. To get Lindelof, you would need to be able to get functional which localizes the sum to kind of isolate individual terms. So because density is t, the interval would have to go like 1 over t, and that such functionals just don't exist. So then the question is, how good functionals can you construct? To how small interval you can localize the S-channel sum? And for that, it turns out that while is the natural barrier. But just to say so the simplest functional, if the functional is just evaluate is just evaluation of the crossing equation at chi is 1 minus 1 over t TL squared. Or maybe I can just write minus 1 over t squared. Then this gives you convexity. I don't think I have time to go through the steps, but it's basically the idea that this chi goes to one limit correctly captures the long average, and if you integrate all the way up to capital T over there, then due to while there are going to be about t squared terms in the sum, and therefore your bound on individual term is going to be off by a factor of t squared. So that's convexity, because convexity is t to the 8 over 4. And to get the while bound, the functional is something slightly more complicated. It's a kind of Fourier transform. So you multiply by it basically uses the fact that in an appropriate limit, the conformal block just becomes an exponential. And then you can do Fourier analysis with this exponential. So conformal block is some complicated function, but because we are taking some large t limit, the conformal block simplifies. These ideas have already appeared in various places in Bootstrap literature, for example, in papers by Slava on Tauberian theorems, and Tradep, of course, on Tauberian theorems. So because the conformal block is like an exponential, you can go to Fourier space and create a wave packet. I'm already out of time. So there is a more complicated function that you can construct, which localizes the left-hand side to the interval capital T minus h, capital T plus h. But there is a lower bound on h. So this size of the interval needs to be smaller than 1/3. If the interval is smaller, sorry, upper bound. If we try to push the localization too small, then we can no longer prove that the identity in the T-channel dominates over everything else. So that's why the while bound is a kind of natural barrier. But okay, there are various other nice results that I wanted to mention. I don't have much. I just want to telegraphically say that one of our collaborators, Anshul Adve, proved recently a remarkable result that these kind of bootstrap, these associativity constraints with discrete spectra actually completely characterize compact hyperbolic surfaces. So in principle, the conformal bootstrap knows everything about the spectra, at least of compact hyperbolic surfaces, as well as theirCijk. So if you apply it to the arithmetic ones, in principle, even Lindelof should follow from the bootstrap, except because we don't know exactly what to do with the bootstrap to prove Lindelof. But it goes some way towards explaining why this associativity idea is quite powerful. So, thanks.
Is there a CFT behind this bootstrap, or it's just the idea of the conformal bootstrap is being applied?
I think it's more the latter for now on. I mean, I hope that long term we're going to extract some lessons out of this, which will tell us what CFTs kind of really are, if they're related to some more deeper mathematical objects than we currently understand. But basically, the representation theory is the same between hyperbolic surfaces or hyperbolic manifolds and CFTs. What differs is the details of how the operator product works. So, for example, in CFTs, we cannot multiply two operators sitting at the same point, but in this world of hyperbolic manifolds, the OP is somewhat more works more generally. So you can multiply two operators at the same point. So there are some small differences which ultimately lead to the fact that CFTs and hyperbolic manifolds are not the same thing, but it's definitely more than just a superficial resemblance, but it's not quite a complete correspondence.
So, would you mind saying a little bit more about this Watson-Ichino formula? How exactly they derive it? More or less the general picture. Yeah.
Yeah. So the starting point is the fact that So I define the triple L function as some Euler product, but there's a formula due to Garrett originally, where it's written as an integral. So you're probably familiar with the Rankin-Zelberg definition of the f1 times f2L function. So they're using all of the Eisenstein series. So there's a similar story for the triple L function, but now it's a more complicated Eisenstein series. And then starting from that, you can prove it basically, and also using this uniqueness of 3-point functions over all GL2QP.
Yeah. So the whole sum is analytic function outside of the cut, yeah?
Yeah. This G of chi is this whole thing is analytic.
Yeah, and okay.
Yeah.
Well, there's some natural physical inputs or optimistic estimates from other like on Bootstrap that you can input and see Lindelof pop out from, or is that not even the case yet?
Yeah, so the kind of input that you would need to just from the single, okay, I probably won't quite answer your question. So the equation is a little bit different from the one in a CFT because you have conformal partial waveguide and conformal block, but I can comment on what kind of input you would need to improve it. It should be to kind of assume something about cancellation in the T-channel sum. Basically, there is some oscillating sum which in the T-channel which we don't know how to estimate any better than some amount, and that ultimately leads to this. Basically, this T-channel sum over everything which is not identity is too big unless this is true. So if we could assume something about maybe chaoticity, cancellations of that sum, then an improvement towards Lindelof would be possible.
Okay. You had 2D conformal blocks at some point. Yeah? So everything is in 2 dimensions, or is it supposed to work in higher?
These conformal blocks are the kind of the one. Maybe it's better to say which group they are for. So they are for SL2, which is true. It's the 1/2 of the 2D group, but it's also just the 1D group. And in general, the conformal blocks that you will find when you deal with hyperbolic D manifolds would be those for CFT in D-1 dimension. So for hyperbolic 2 manifolds is the CFT1, so just SL2, or holomorphic half of, or 1/2 of the CFT2, if you wish. Yeah. For hyperbolic 3 manifolds, about which we also had a paper that I didn't talk about, the kind of blocks that you have are the global blocks in 2D.
Okay.
There's one more, yeah.
Is there any generalization in the direction of L functions analogous to higher dimensional hyperbolic manifolds?
Yeah, yes, there is. So, well, the ones that I would define it for this degree D. So they would arise naturally from from quotients of the kind of higher rank analog of hyperbolic space, which usually comes from GLD. So they're of course, they will come from automorphic forms on GLD. Higher dimensional hyperbolic manifolds correspond to a different group, which is SO1, D+1, and you can also define automorphic forms for those. So for example, there is a nice group, SO1, D+1 over Z, for example, which gives you a nice quotient, and so on. So, but this kind of Langlands stuff is much more developed for GLD than for that group, but I think quite a lot is known also for that group.
Okay, well, thank you again, Dalimil.